Let's work through an old exam question about electricity. Remember that if you find this useful, please like and subscribe so that I know that I should make more movies like this and that you will get notifications when I've done so. So we're going to today go through question 8 of the 2019 National Final Exam. And in this question, we have a circuit. We're given a graph that shows us that the EMF of this battery is 13 volts. How do we see that? Well, from the graph we see that that is the potential difference across the battery when the switch is open. In other words, when no current flows through the circuit. That is one way we can define EMF. EMF is the potential difference across a battery when no current flows through the battery. Another way to define EMF is that it's the voltage, which means energy per coulomb of charge, the maximum energy per coulomb of charge that a battery can give. So it's the maximum work that a battery can do on each coulomb of charge. We see from the graph that the EMF of this particular battery is 13 volts. Now we also see from the graph that as soon as we close the switch, so that current now flows through the battery, the voltage across the battery drops to 10,5 volts. So the terminal potential difference is then 10,5 volts. And the terminal potential difference is also equal to the external voltage. And in this case, because a very simple circuit, we only have one resistor in the external circuit, then we know that the voltage, the potential difference across that one resistor is also 10,5 volts. And that drop from 13 volts down to 10,5 volts tells us that there is battery internal resistance. There are some lost volts. The resistor of the battery is taking away 2,5 volts. And that's why we get a drop from what the maximum the battery can give to what the actual that the battery gives to the circuit. Now, we are first asked a very easy question, and that is we have to calculate the current strength through that resistor. Obviously, since it's a series circuit, the current strength throughout the entire circuit. And we know that that is equal to the potential difference across that resistor divided by the resistance of the resistor. So the only trap that you might fall into is by putting that 13 there. That would not be right because there is not 13 volts across that resistor. Rather, it is 10,5 volts when the current is flowing and the resistance is 5,6 ohms. And so we do a very simple calculation with our calculator. 10.5 divided by 5.6, and we find the answer is 1,875. And because it is a current we're calculating, and this is volts and that's ohms, the answer is amperes. And we might round that off to 1,88 amperes. But don't clear your calculator. In fact, we should put this full value into the memory of our calculator because we're going to use it later. So how do we do that? Shift to activate the yellow parts and then recall, and actually then we are really pressing store, which is in yellow above it. So we're going to store it into one of the variables. Let's store it into variable A in red there, so we can easily recall variable A whenever we need it. Now the next question is also very easy. We're asked to find out the power dissipated through that resistor. And we know that power is equal to V times I, or else we could take I squared R, or we could take V squared over R. Any of these will give you the correct answer, obviously, as long as you substitute correctly. So the voltage must be the potential difference across the resistor, 10.5, not 13. And then the resistance, we know, 5,6, and the current strength is 1,88. So let's use the first version, the voltage 10,5 volts multiplied by the current strength through it, 1,88, remembering that that's not actually the correct number. Let's rather use the full number, and since I haven't yet cleared my calculator, I can simply use that. Otherwise, you can press recall A, and then it comes up. Multiply by 10.5, and we get 19,6875, which we round off to 19,69. We must give the correct unit. What are we speaking about? Power. What is power measured in? Watts. Next, we are asked to find the internal resistance of the battery, small r. Now, we know that the EMF that the battery gives is distributed between the two resistors in the circuit. That one and that one. The internal resistance and the external resistance. So the EMF is equal to the voltage taken by the internal resistance plus the voltage taken by the external resistance. Now remember, we are trying to find little r. We don't yet have little r in there, so we need to do some adding of information there. We know this is 13 volts, and V internal is made up of I multiplied by small r. We know the value of V external is 10,5. So we substitute that in. We also know I. We calculated it over here. So then we only have one unknown value, the one we're trying to find out. So let's substitute I, which is 1,88. Now it's just a matter of algebra. So let's get the r to that side and all the other values to this side. So we must subtract 1,88 r from both sides, and we must subtract 13 from both sides. That gives us 10,5 minus 13, which is minus 2,5, is equal to minus 1,88 r. Let's divide both sides by minus 1,88, and clearly the minuses are going to cancel away. Again, it's not really 1,88. Let's use the full number. 2.5 divided by recall A, and we get 1,33 recurring. 1,33. What are we speaking about? We're speaking about battery internal resistance. What is its unit? Ohms, because this was volts divided by amperes. Volts divided by amperes is ohms. So now we have the value of that internal resistance. It is 1,33 ohms. Question 8.4 says that now we add a parallel branch consisting of two resistors of equal resistance called X. And what we have to answer is what is then going to happen to V external, the terminal potential difference or the potential difference across the circuit. Now, when you get a parallel circuit, it helps to simplify it as a series circuit by replacing the parallel section with an equivalent resistor, a resistor which has the same effect as the whole parallel section, but that's just one resistor. So let's just do that. Let's draw that and then think this thing through. So let's draw here. Before we have X, well, actually 2X added, and after 2X has been added. And in both cases, we have an EMF of 13 volts. So I'm trying to show that they have the same voltage as one another, the same EMF, by writing that symbol the same size. And then in both cases, they have internal resistance of small r, and that is also the same between each. So I'm trying to write that small r the same size for both. And then before we have the parallel circuit, the parallel section added, it's very obvious that we have a series circuit with just a resistance of value 5,6 ohms. Afterwards, we don't really have a series circuit, but as I said, we're going to simplify the circuit to its series equivalent. And so here we have R parallel, which is the series equivalent. Now, how does R parallel compare with R? Is it greater, less resistant, or the same as R? Adding resistors in parallel decreases overall resistance because it gives more paths. So the charge can flow easier because there are more paths to choose from. And that's why it's easier, so there's a lower resistance. So I'm going to write R parallel small, smaller than R, implying that that value is less. And that is the key to being able to answer this question. So we understand that a battery has EMF, which it supplies. It's supply voltage, supply energy per coulomb. And the resistors in series, or in effect in series, within the path, receive that voltage from the battery. And between them, if they're two, as we have here, they have to share that voltage. How do they share that voltage? They share it according to their relative resistance. How resistant they are compared to the other. Or we could say compared to the whole. So can you see that although the resistance of the internal resistor has not changed, the relative resistance, how much it makes up of the whole, has changed. Here, because the total is less than there, this one makes up more relative to the whole than it did there. And so it will take a greater fraction of the supplied voltage. So V internal here will be greater than V internal there, because here that internal resistance makes up a greater fraction of the whole resistance because the total resistance is less. But if you don't like that way of doing it, let's go the equation route. We are trying to compare what has happened to the V external, because that's the question, from that situation to that situation. Is it increase, decrease, or stay the same? So V external is our focus. So we know that V external is equal to the EMF minus the V internal, which is made from IR, or which we can calculate from I multiplied by R. Okay, let's compare this situation to that situation. Here, the EMF is the same value as there. I is not the same value. We are told that here the current is greater. That makes sense because we've decreased the external circuit's resistance by giving more paths. And so the current can flow more easily. So the current strength here is greater than there. But the resistance of the battery internal resistance is the same. I'm trying to write the R the same. So we can see that, of course, here there's more to subtract away, which is the same as saying there's a greater V internal. So that leaves less for the other resistor here, V external. And so from that we can see V external decreases when we add more resistors in parallel. That is only true though if there is battery internal resistance or another resistor in the main part of the circuit, so that there can be this kind of seesawing of the voltage supplied by the EMF between the parallel section and the other resistor that's in series with that. Now we go on to the final question, point 4.2, where we are asked to find out what is the value of X. How can we do that? Well, if we could find out RP, the equivalent resistance of that parallel section, then we could decompose that and get out just X. So how do we do that? Well, we can make use of this equation here because we know this value, we know that value, we know that value, we calculated it here. And so we can find out V external. Well, that's not quite what I was asking, but remember, V external is I, that same I, multiplied by RP. So then we can solve for RP. Okay, let's give this formula in the format that we're a little bit more used to with it probably, which is the EMF is distributed between the internal resistance, the lost volts, and the external resistance. Of course, that's not directly helping us because remember, we really actually want to find RP. So we need to then put in our information and decompose that into that. So we know that this is 13 volts. Remember that this is actually referring to that situation after. Right, so the internal we know is I times little r. Both of those we know. We're going to substitute just now. And the external is I, which we know, times R parallel, which is what we're trying to find out. Let's substitute these values. I is 4 amperes. Little r is still the same, 1,33 ohms. 4 amperes, and we are trying to find out RP. So let's do our algebra. So we need to subtract this value from both sides. So we have 13 minus 4 times 1,33 is equal to 4 RP. Or we can just skip a step maybe and divide both sides by 4. And then that will give us RP. So let's get our calculator. 13 minus open bracket 4 times 1.33 close bracket equals this value that we have on the calculator, 7.68. Can you see? It is actually V external. And now we're going to divide through by 4, and then we're going to find just RP, and that is 1,92. Don't forget the unit. It's a resistance, ohms. Right, but remember, that is not actually what we were asked. We were asked to find X. So we need to continue. And we know that when we have two resistors in parallel, two parallel branches, then we can make use of this equation. The equivalent resistance of the parallel branch is equal to the product of the two branches divided by the sum of the two branches. You can only do that if there are two parallel branches. Now we remember that R1 is 2x and R2 is 5,6. So we simply substitute 2x times 5,6 divide by 2x plus 5,6. And we know the value of RP. It's 1,92 ohms. So let's multiply both sides by 2x plus 5,6. 1,92 multiplied by 2x plus 5,6. And of course, when we multiply this right-hand side by that, that cancels, getting rid of the bottom of the fraction, leaves 2x times 5,6. Let's multiply that one through. 1,92 times 2 is 3,84 times x is obviously 3,84. X, don't forget the x, plus 1.92 multiplied by 5.6, 10,752 is equal to 2 times 5.6 is equal to 11,2. Again, don't forget the x. Right, let's get all the x's to one side. Easiest if we don't need to have a minus. So let's get them to that side. So we have 11,2. I could write it out, but you simply subtract 3,84 from both sides. Let me just do that straight. 11,2 minus 3.84 is equal to 7,36x, don't forget the x, is equal to 10,752. We divide both sides by 7,36. I have that on my calculator, so I simply press invert and then multiply by 10.752, and that gives me x as 1,46. It's a resistance, it's ohms, that is the value here. You should go and check this. Take this value, put it over there, multiply it by 2, add them together, and that then gives you R1. 5,6 is R2. Substitute all over and check that indeed you do get a parallel resistance of 1,92. That will assure you that you didn't make any algebraic errors over there. Notice you should also be able to solve this, and you can go back and also check it this way, using instead this formula. 1 over Rp is equal to 1 over R1 plus 1 over R2. And again, R1 would be twice that. Well, in the beginning, you don't know that. It would be 2x. Plus 1 over R2 would be 1 over 5,6. So that takes us to the end of this particular question. Remember to like and subscribe and leave comments below of what other topics you would like me to answer in this same way as you prepare yourself for your exams. And as you do so, all the best.